I manage? I think I got. Did I give this to everyone? The homework sheet? Or did I get interrupted? Ever get the homework sheet? You'll let me. All right. So homework one tonight is on the first section of our new unit, which is on differential equations. So we're just going to do kind of a little intro to differential equations in this course. The parts of differential equations that AP would care that you know. But obviously, if you have a great interest in this, you'll go on next year and take multivariable calculus in the first semester, and then we have a whole semester course called differential equations. So you'll get a taste of what that course is about right now, even today. As usual, there we are with our cool noodles. Right, we got to incorporate those somehow. And right now, at least, maybe we should come back to this and look at this later. But right now, maybe you don't understand what you're looking at, but I promise this will become like a tool that you're looking at. It's called slope field that you'll become very, very excited about later another day. So, and we're drawing various solution curves with our pool noodles. We think we're great. Just a broad overview. This is the kind of overview that we gave you first semester when we handed out the syllabus, but I thought I'd just share again kind of where we're headed. This is a little bit of a shorter semester in terms of content, just because first week of May is like when we need to be done, and you need to have all the knowledge in your head and all the abilities. You need to have complete calculus mastery by the first week of May. So this is where we are right now. Differential equations is what we're about to engage in the next few minutes even. Applications of integration, Unit 8, which includes all sorts of fun things like finding the volumes of crazy shapes and things like that. Series and sequences is don't believe what they say. Okay, and then vectors and polar calculus. Both those last two units, historically people do sometimes find more challenging. So, but that's okay. When you're there, you'll be ready. So you'll be ready. And then we'll be reviewing, of course, for the AP exam. We have like kind of a whole unit. We really count that kind of as another unit, really, where we have during that time AP problems and practice free response questions and all the crazy. We'll explain more when we get there, but don't worry, you will be, when the time comes, you will be ready for the AP test, don't worry. Okay, good. So today's lesson in the first section of this chapter is called Initial Value Problems. And I think it's a pretty nice way to start us off here. So recall the very simple fact that this is true, right, for this particular function. If I hand you a derivative, and really, that might be right now what you call it, but honestly, if I hand you this, y prime equals 2x, that is an equation, isn't it? And we might call that, well, since it has a differential in it, we might call that, even though it's the most basic, the simplest possible example of it, we might call that a differential equation, right? Because it's an equation that has a differential in it. And notice that by saying y equals x squared plus c, in some sense you're saying what y is. So this is a new level of abstraction for the calculus student to engage in. Back in algebra, you had equations that had solutions, and those solutions were numbers. Well, now we're encountering equations whose solutions today, and as we go through this unit, whose solutions will be functions. Functions that satisfy the equation. Now, I know you've never had that thought when you looked at this as being like, oh, that's how I think about that. But really, that's what we're dealing with. We're dealing with an equation that has as a solution some function y equals f of x, right? Now, we would call this the general solution because it has a c in it still. But if someone wanted to, they could tell you more information and you could actually nail it down. Like literally, instead of having it slide up and down vertically with a c value, you can actually nail it down with some value. So for example, here's how the problem might come to you. And this is your first example of an initial value problem, right? And the reason it's called an initial value problem is because we give you a differential equation, in this case it's a super simple one, along with initial conditions, initial values, boundary conditions, sometimes people call them. So by find y, I mean do what we were just talking about. Find y equals f of x. Give me the function that makes this happen, for which this is true and this is true. All of this is true simultaneously. Well, go ahead and I have every confidence that even though we've never done one together, that you can just do it right now. Name the function that makes this happen. So I guess we already gave you the general solution, so that made that part not too bad. And then what'd you do? Obviously, I think most of you reached for this. Go ahead.
The y and the x.
Yeah, okay, so he said, I think to quote him, you put your x and your y in, and you get your stuff, and then it works, he said. Yeah. So that's essentially right, even though maybe loosely put, right? It should be clear that C is 3, and then there's our solution. Not too bad for your first initial value problem, right? Obviously, we can make them a little bit trickier, but we don't have that intention today, at least. So again, just to be clear, this is our first example of an initial value problem. And the thing we encountered at the beginning is called a differential equation. And when a differential equation is presented to you along with initial conditions, we call that together an initial value problem. And the reason this is like an important thing, by the way, you'll learn, especially if you take differential equations, is that that's often how we model things in the real world. A lot of times we don't have like a function we're looking at. The thing we know and understand and have modeled is actually some kind of relationship between rates of change, actually. We understand that the friction is directly proportional to the velocity, right? Okay, well, how do we get from that to the position? Well, we need to give some initial conditions. A lot of times what we have is not position information, it's like velocity information, or maybe it's in the economic situation, maybe we don't know about the cost, but we do know about the marginal cost, that is the change in the cost, right? Something like that. So we often have differential equations we're working with when we're modeling things in the real world. So you'll see lots and lots of great. I should really, at some point here, I'll pass around one of the differential equations books, and you can take a look at the kind of many different applications that are cool that you can give a try. So let's try a slightly harder one. It's not really meant to be that much harder. It's really similar to problems you've just done in the last unit. Except for the initial value part, right? That's maybe feels a little weird. So take a minute with your table of invariances when you're done. I guess I should have explained what first order differential equation means. By first order differential equation, we mean one that has a derivative, first derivative in it, that's all. Right? The highest derivative is a first derivative. I guess that kind of foreshadows what might come later. So integrating both sides gives e to the t minus 2t cubed, yeah, plus some initial value, some constant there. And then plugging in, let's do this carefully, we get what, 0 equals e to the 1 minus 2 times 1 cubed plus c. So c is what, 2 minus e? Yeah? All right, well then I think we're done. Let's just write this out, right? X of t equals e to the t minus 2t cubed plus 2 minus e. Put a box around it maybe. All right. So far, I think you've understood why it's not too bad to solve a differential equation of the form derivative equals some function of x or in this case t, whatever, right? Because all you have to do is integrate both sides and then do what Luke said, put stuff in, and whatever, right? Let's try a second order differential equation as well. Notice what, or I should ask, what do you notice about the form of the question, too, that needs to be practical? Maybe you don't even yet realize why this is necessary, but what did I give you in the setup? Besides a second order differential equation, I also gave you when x is 0, y is 1. But I also told you when x is 0, y prime is 0. So I've actually given you like kind of two pieces of information instead of just one. And you might think, is that necessary or no? Well, the actual calculus involved here is not super heavy, right? What's dy dx? If we integrate both sides, that is, if we undo one derivative, I guess you could say. Yeah, negative cosine x would be the antiderivative plus some constant c. Okay. Yeah, there are a couple ways in on this, but we could. What do you want to do next? I'll offer it to you. What do you see? Would you like to do it again right now, or no? You want to just take one more derivative right away? You'd be welcome to. That's fine with me. In which case, we might want to call this. Maybe you see it already. We might want to call this. How about C1? Is that okay? Okay. So I'll welcome that move if you'd like to do that. So go ahead and tell me, what would the antiderivative of that be? It's negative, what is it? Plus, well now keep in mind C1 is a constant, so what's its antiderivative? I hear mumbling, but what, yeah, go ahead. C1x, right? It would be, it's just like if the number 5 was sitting here, you'd say the antiderivative is 5x. So C1x plus, call it C2. Okay, that'd be fine. So this would be one way to do it. You call that maybe the general solution. But just to be clear, you could have resolved this constant right away up here, couldn't you have? In fact, we can go back to this equation and do it right now. What is C1? Well, which thing is helpful up here? What are we doing? Yeah, plug in 0 for x and on the right side. And you should get 0 over here, is what I guess that says. Okay, so if we plug in 0 on the left for the derivative, which is apparently what we get, and we plug in 0 for x on the right, I think in a second we'll know what we really mean by C1. Cosine of 0 is, so I think C1, that'll be a negative 1, so that I think C1 will be the number 1. So really, that's a nice constant. I like the number 1. Really, by C1, we really mean 1. So we have this as our differential equation, as our solution. It's still general, and we'd like to apply the initial condition that we also still have. So if you have, a lot of you maybe already done it. Let's do it together. 1 is y, and x is 0 again. Well, that's a nice one, isn't it? Looks like C2 is also 1. All right, so I think we should write it and put it in a box, shouldn't we? Y equals, all these constants are conveniently 1. That's exciting. It's very nice in this unit to be able to go back and be able to check your solutions, right? If I have a purported solution, you can check all the things that were claimed about it are true. Check that its second derivative. Go ahead and try. Check that its second derivative really is this. Right? Check that if you take its first derivative, that you get, and plug in 0, you get 0. Or that in the original function, if you plug in 0, you get 1. You should be able to go through and just verify that it really does work. In fact, even when we get into the worst differential equations ever, even if you don't know how to solve it, if someone comes along with a purported solution, it's very easy to check whether they're right or not, even if you couldn't yourself produce that solution. So let's give an example where we might think about differential equation as well in a context of rockets. It's very appropriate. Take a second to just digest the problem and then engage in it. doesn't seem like we've handed you, doesn't seem at least immediately that we've handed you the things we need. Like, where is the differential equation? What, I mean, how can you even do this? In some senses, we're about to kind of be Newton, right? We're going to take this assumption of constant acceleration and then just like do everything from first principles, right? You have a way in? I'd love a differential equation. You have it. There is a very, very simple one that's like ready to be written down if you have it. Take it away, Maddie, if you have it. All right, I think you're already writing down the velocity. Is that what you said? The velocity? Okay. So that isn't a differential equation, but you may have already solved the problem. Good job. You're like, I don't need this differential equation. I'll just solve it right away in my head. Do you have a differential equation now? No, you were going to say what she said. Yeah, that's great. I do think I have. I do think this provides for me a very, very simple, and so simple that maybe skipped over it. A very simple differential equation. If we mean there's a constant downward acceleration, then how would we write that? Let's give some letters to some things. Let's call, I don't know. Do you want to call y the height? Y is the height. Velocity we'll call v, and we might call, I don't know, we might call the acceleration a if you like, if you want names for those, but you don't need names. I'd really like to maybe just think about y. What is 9.8 meters per second squared? What is that? That's the constant. The acceleration is always that number. How do you write that down as a differential equation? Yeah. Yeah, one way would be to write a equals negative 9.8. Or, said another way, in terms of y, yeah, the second derivative of y equals negative 9.8. So you can see, again, I think I emphasized this earlier, but a lot of times this is the context that we encounter in the real world. We're like, well, I don't know about the actual motion of the spring, but I do know like how it responds to forces, right, or something like that. Or I don't know the actual characteristics of a certain probability distribution, but I do know how it changes as we move from left to right or something like that. We often know about changes. And so that's the very simple differential equation we're dealing with. And I think everything else can kind of just fall out of that. So you see, that if someone makes that observation that there's constant acceleration, everything else is just going to happen. Are you ready? This is a very exciting moment, right? So what's dy dt? AKA v. That is the answer to A. Can we do this? It's negative 9.8 t, to use our independent variable, plus a constant, just for fun, do you mind if I call that constant, I don't know, v0? Is that okay? I mean, it's just a constant. You can name it anything you like, but I already kind of know what that means in my life, don't I? Okay. So, yeah, maybe that was kind of giving away the game a little bit. I apologize. But it's a constant. So, and then it doesn't give us information to actually help us solve for that. Apparently it does, because Maddie already did it. So, initial velocity of 160 meters per second. Let's play dumb and say we didn't know that. Okay, that's the v0 there. We might be thinking, well, what is v0? Well, when t is 0, we need to have this be true. Well, I think if you didn't make it, if it wasn't obvious before, it should be obvious now that v0 needs to be 160, right? All right, I think we're finally ready to write down the answer to A. Again, we probably spent much more detail on that than you probably wanted, but it's negative 9.8 t plus some constant, which we have now just certified is 160. Verify that that does satisfy the constraint that the acceleration always be a downward at 9.8 meters per second squared, and that the initial velocity be 160. I think it meets both of those. And then, of course, to get the height, I think this will be fun. The height is equal to, or what are we calling it? Y, I guess, sorry. My apologies. You can call it whatever you like. Is simply, well, how do we go with that one there? It'll be negative, yeah, whatever half of that is, negative 4.9 t squared plus v0. I guess actually we know v0. It's 160, so we'll just write 160. (160t), the antiderivative of 160, plus, well, okay. Let's pretend we don't know what it is yet, but it would be like some constant. We might call it y0 or something. And then I think, maybe it goes without saying that if you plug in 0, you need to get 3, and so that just gives away that y0 needs to be 3. So I guess I'll just go with it. People are like, just move on. Okay, all right, I'm good. I'm good if you're good. That's the answer to B then also. So I hope you appreciate it. If you haven't stopped to appreciate it before, I think there might have been a time in your life where you've appreciated this already first semester. But the fact that A is equal to the second derivative of y with respect to t, I guess we'll say, and that equals some constant g, the fact that that gives rise just automatically to the following things, just because of how calculus just has to work. I guess we're using y, yes. Right, like these are formulas that someone might have handed you in like a pre-calculus or maybe even in an algebra 1 context. You might have seen this, right? When you were doing like a parabola is like the proper model for a football being thrown through the air. Or, I don't know, in your algebra 2 or something. I don't know when you would have done projectile motion. Someone would have just handed you this and be like, just use this. It's a parabola. It works. Just shut up and use this equation. But now I hope you see why, like, there's a great explanation for that. And you might have been like, why is there a 1/2 in there? Well, you, calculus student, should be able to very thoroughly explain why this equation looks the way it does, doesn't it? I just anti-differentiated twice here from this very, very easy first assumption. Okay, so anyway, pretty simple problem, but in the end I wanted to make sure that you heard that. Okay, so our lesson today is intentionally just a little short, just a nice, easy intro to initial value problems. Does anyone, can I collect the red cards? If you have, you need more, you can hold on to it too, like I said, if you like. You're gonna do some soul searching on that. Okay. Because I thought maybe today we'll one or more items of your bucket on your bucket. It could be more than one something like this. This might be like too much. Graduation. Very calculus and stuff like that. You're not ready. You're thinking about it. I guess I should have invited you before we even got too far into today's class to meet the people at your table, but maybe, I don't know, you know people there in this class. Sometimes I don't have a good sense for that. You guys all like know one another as well, but maybe. I think especially in math class it's good to meet one another because like these are people who are not in your grade necessarily. You know, there are lots of grade levels, likers of RM here. Well, as a way of meeting just a few people, and then, like I said, please apply some pressure later for us to go through some of these later too. Let's meet a couple people. Let's start down here. All right. This person is Raina. Hi. Everyone say hi, Raina. Hi. Hi, Raina. I'm sure everyone. Are there other people who wrote this? This is kind of like the thing you write, right? I should have said no writing this, but what did she write? What do you think? Oh no, everyone has different things. It says go skydiving. Do you really mean it though?
Well, like I like heights. And I like not feeling the ground under me. So
Those are two things that would lead someone to want to skydive. I think.
Yeah.
Yeah.
So the obvious conclusion is go skydiving.
And you also want to go to Harvard.
No.
Okay, you're just wearing the shirt.
I took it to my sister.
Oh, okay.
Competition.
It's cool. All right. Here you get to. It's nice to meet you. All right, Kathy D. We get to meet. Put her. That's Kathy D. Everyone. We have three Kathy. I don't know, like I said, everyone says go skydiving. It does say that as the first one. The second one says is visit Europe. I like this. And another one is attend another concert.
Yeah.
You've only been to one?
I've been to one, and I want to go to one.
Any particular artist? Or
I don't know.
huh? Or group?
A lot. That whole movie.
Give us a recommendation though. Where are we gonna see you if we go to a concert? Where is this gonna be?
Halsey.
Huh?
Halsey.
Halsey. Okay. Europe's a big place. Any particular place you want to go?
I just like I've only ever been to the United States and China, so I just like anywhere.
You're covering your bases, but yeah, there are a few other conferences we hit. That's good. All right. I like these. I like this more than just like what are your interests, because it's like also tells me like what you care about in that sense, like what your future passions are. Oh, that's hard to read here. This is Liam. Everyone say hi, Liam. Right. And
You want me to read it for you?
yeah, please. And something about a band. Right. Wait, this is actually kind of fun. Write a song with a band and perform.
Yeah.
Okay. Write and perform a song with a band. Are you in a band right now? Yes, I will.
I have a loose group.
Okay. What's the instrument you're playing? Okay, guitar and vocals. Okay. So you want to do like drums? You got bass anyway?
I have a bass.
Okay. All right. Good. Well, we're trying to help you here. Okay. What do you play?
Yeah, no, but
Yeah.
that's
You need a
like
pianist.
I have a pianist too.
Okay. What kind of music are we talking about?
All rock, psychedelic rock, bluesy,
What was the first thing you said?
alt rock.
Oh, alt rock. Okay. And, all right, that's good. So if you're into any of those things, see Liam. Okay. He's looking for winter auditions. I'm putting words in your mouth. Sorry. But that's cool. I mean, hopefully we'll see you someday and like we'll say we knew you when. We'll remember your calculus teacher. Okay. Okay, Kevin, where are you? Sorry, I'm still. Kevin, hi. Everyone say hi, Kevin.
Hi, Kevin.
Nice to see you. He wants to. This is interesting. I like this. Live in San Francisco. It's like on the bucket list. It's like not just go and visit. Live.
Live, stay there, nowhere else.
I feel really strongly about this. I like your determination. The other one it says is become an. Didn't know this was going to be difficult. And it says you don't know either? Good. I just want to make sure. An engineer. Okay. There are more letters in that word. Is that right?
I don't know, I rushed at the end because of the question.
Okay. Become an engineer in San Francisco.
Yeah.
Yeah, do both. You can do both at once. That's good. You don't want mutually exclusive goals, so that's good. There's a famous mathematician that said, this is kind of nerdy though, but they said they were suicidal, and they were like, well, I want to commit suicide, but I also want to like get my doctorate in mathematics. And he's like, but those things don't commute. It's hilarious. Right? It's like I can't do. There's a certain order I have to do these things. Right? Like, those don't commute. I can't do I can't pick the order there. Like I have to get my PhD first. So I don't think he ended up committing suicide, but it's still funny. It's or maybe it's it's big. All right. Okay, this will have to be the last one, I think. Dewey? No, where's Dewey? You're Dewey. Somewhere over there. Sorry. It's actually somewhat. I'm trying to tell you people I've had before. It's not. There are a lot. I know a lot of you from pre-calculus, but not you. I don't know who you are. This is good. You want to study graphic Design. Okay. Cool. Not Mac? Might be like still something I can convince you on though, maybe, huh? Mac, double maybe. Okay. Good. Do you have a school in mind that you like would be like the school of choice? You like? Cool. All right, nice. All right, we'll save some more for another day here, but it's good to meet you guys. And we'll have fun. I know this semester learning some more calculus. On your way out today, the bell's gonna ring. We still have about a minute, but on your way, you can just drop your stick in the cup if you will.